specific, as I said, a specific class of differential equations known as linear differential equations. So that would be an equation that would look like this. There's some constants, and then there's a little notation here. Well, let me write let me clarify that by writing what's over here. And now I've already written the first derivative and the second derivative, and so I get tired of writing all these little marks, so I put 3 here. So by this I mean the third derivative, and by this I mean the nth derivative. So that's the general form of this type of equation. And to solve it, we're going to try a solution of the form y equals e to the rx, where r is some constant. So if I plug this in over here, I get a0 e to the rx equals 0 plus. Now when I find the first derivative of this, it's just going to be r times that function. So we have a1 r e to the rx. Here the second derivative, we're going to get r squared, right? So it's r2 r squared e to the rx, and so forth. a3 r cubed e to the rx. So when I get all the way up here, what do I have? I'm going to have a to the n, a sub n, r to the n, e to the rx. Imagine, if you will, this is a perfectly straight line. Okay, so the next step is I want to multiply both sides by e to the negative rx. Well, e to the rx times e to the negative rx is 1. So I have a to the n, r to the n, plus all these in between, a3r cubed plus a2r squared plus a1r plus a0 equals, of course, 0. Okay, now I want you to, in your mind, substitute for r here an x, because I want you to think of this as a polynomial in x, or whatever letter you prefer. And what I have here is an nth degree polynomial. So the question is, how many roots does an nth degree polynomial have? I know I've asked this before, so I know there are people who know the answer just like that. And this is the fundamental theorem of algebra. How many roots do I have? N Yes. So I know that there are roots, I'm just going to call them R1, actually, R1, R2, all the way up to Rn. So these are R's that will set this to 0, which means that I have solutions to the original differential equation, y equals e to the R1x, e to the R2x, and to the R3x, all the way up to e to the R to the nx. Now, if you go on in mathematics, you're going to get very comfortable with the idea that when I put something up here and I go from 1 to n, you're going to get very comfortable with that idea. But if you're not comfortable with it right now, just think of this as a2 to the second derivative of y plus a1 times the derivative plus a0 times the derivative. And the polynomial is just a2r squared plus a1r plus a0. It doesn't really hurt to add all these extra elements. And then there's just two solutions, R1 and R2. We're going to have a practical example, so you'll see how that works. Okay, so we have n solutions to this equation. But I want you to look at something. Let's say I have some solution to this equation, all right? If I multiply this through by a constant, let's say c, let's be consistent here. What does that tell me? Well, cy, the derivative of cy is cy prime, right? The second derivative is c double prime y, and so forth. That is to say, if y equals e to the R1x is a solution, and y equals c e R1x is also a solution. That is, you can multiply any of these by a constant, and it's still a solution. That's a feature of it being a linear differential equation. Furthermore, if I were to take the original equation so let's say y is R1x, and then I have another solution, z equals R2x. So here I have a sub n z to the n plus 2z double prime plus 1 z equals 0. Z is another solution. If I add these together, I find that the derivative of y plus z is the derivative of y plus the derivative of c, and likewise for the second and the nth derivative. Well, this tells me that if y and z are solutions, y plus z is also a solution. This is a really important feature of a linear differential equation. In fact, if I have a series of solutions, any linear combination, that is, if I have a set of solutions, e to the r1x, e to the r2x, e to the r to the nx, and y equal some constant a1 e to the r1x plus a2 e to the r2x plus all the way up to a to the n to the rnx. Again, these are just arbitrary constants. Then this will be a solution. This is what I mean by a linear combination. Sum of the solutions times some arbitrary constant. So this is, one of the reasons this type of equation is so important. It has a very straightforward solution. If we have the equation in this form, all we really need to do to solve it is to solve this polynomial, which we have some capability of doing, right? Let's just take a look at a few simple examples. If n is 1, that is to say the equation is y prime, say a1 y prime plus a0 y 0. Well, we have a polynomial here, a1r plus a0 equals 0, which we can solve very easily. R is just negative a0 over a1. And that tells us that the solution is e to the negative a0 a1r, x, right? Furthermore, we can just put some arbitrary constant in front of that. Okay, that's nice. What about for n equals 2? For n equals 2, we have an equation a2, second derivative of y, a1, first derivative of y, a0, y equals 0. So the polynomial is a2 r squared plus a1 r plus a0 equals 0. And we certainly know how to solve this, don't we? What would we call that magic formula? The magic formula that lets us solve this? There are murmurs. Okay, this is the quadratic equation, right? Quadratic equation says solution is negative b, which is this guy, plus or minus the square root of b squared, minus 4 ac, all over 2a. So we could write the general solution to this without knowing any of these constants. That's quite fantastic. Y equals, I'll just say capital A, e to the a1 plus the square root of a1 squared minus 4a2 a0 over a2 plus b, e to the a1 minus square root of a1 squared minus 4a2 a0 over a2. Okay? That's pretty exciting. I mean, you don't have to do any work, right? The answer's already there. I'm just curious to know, does anyone here know what happens when you have a third degree polynomial? Can you always find the solution to a third degree polynomial? Deficiency in your education. Okay. Small digression here. Quadratic. Well, okay, so first degree polynomial, right? Just 1x. I think it was it was known how to solve this before the Middle Ages, but basically algebra was developed in the Middle East in the Middle Ages. So we would probably credit them with this. And also second degree quadratic formula. Third degree, well, there's special cases, you know. If you can factor it easily, you can, find the solution. But it wasn't until the 1700s that a general formula was found for a third degree equation. You can look it up. It's a very ugly formula, but it does always pop out the solution. And soon after, they found the formula for a fourth degree. And everyone thought, aha, this is great. We're gonna be able to solve all these equations with just a formula like the quadratic formula. Ugly, but it works. So they started looking for a fifth degree formula. Now, of course, like any other polynomial, there are fifth degree polynomials you can get the exact roots for. Oh, I put a check mark here. It doesn't belong there. Question mark. So for, I guess, about 100, 150 years, I'm guessing, this question was an open question. Is there a solution, general solution to the fifth degree polynomial? And a gentleman by the name of Galois history of mathematics is littered with mathematicians who do something fantastic, and then by the time they're 25, they're dead. And Galois fits this. Another more recent example is a fellow named Ramanujan, who I think it's in the early part of this century, same deal. Brilliant, groundbreaking work, and then he's gone. Not everyone does that. Erdős, probably the most prolific mathematician of all time, only died, I don't know, a dozen years ago. He was in his 80s. Fantastic mathematician. Okay, so anyway, Galois, what did Galois show? He showed not only is there no general formula for this, there's no general formula for anything over fifth degree. And he showed why. But that's not really what was important about what he did. What he did was he developed an entire branch of mathematics, which we call group theory, which is part of what we call modern algebra. And he showed that while we know fifth degree polynomial has 5 roots, there is no general formula for it. In fact, he showed that there are polynomials that you can't express the roots in terms of just numbers and roots. So there's some weird numbers out there, irrational numbers, that, if you look like a plus, b times square root of c, they don't have this form. You can't find a solution. Okay, digression is over. Back to differential equations. So, okay, so up to, for us, up to a second degree, it's solved, and in reality, third and fourth degree. Third and fourth degree. Now, there's a little more to look at here. I'm going to convert this back to the form you're more familiar with, which is, the quadratic formula is negative b plus or minus square root of b squared minus 4ac all over 2a. Now, does anyone recall the name we give to b squared minus 4ac? I mean, this is an important quantity because it basically has 3 types of values. This can be greater than 0, equal to 0, or it can be less than 0. You recall what this is called? Okay. Well, we call this the discriminant. I guess this must be a really odd word because when I type it in on my old Word 2002 or something, it gives me a spelling error. I've never heard of this word, but it is a word. Actually, I'm not even sure if there's an E or an A there. I think it's an A. But either way, it says there's an error. So the discriminant tells me, does this have 2 real solutions? 1 duplicate root, right? If this is 0, right, plus or minus 0 is just the same root. Or if it's negative, we get what kind of solution? Loud. Irrational. Is that what you're saying? Irrational? No, actually, you can have an irrational solution up here if this number isn't a perfect square. I'm looking for something a little different. You're on the right track, though. The problem is the square root of a negative number, right? All familiar with imaginary numbers that aren't really imaginary any more than any other numbers? Yeah, if this is less than 0, you get a complex root. Now, you might say, wait a minute. If I have a complex root, and my solution looks like this, a plus bi times x. How do I do it that? Well, that's e to the ax times e to the bi x, okay? And e to the a, that's just some number, so that's not a problem. It's just, we'll just call that, say, capital A to the x. And again, this is just e to the b to the ix, so we'll just say e to the b ix. Actually, I probably want to leave that e to the ix. Does anyone know what you can do with that? We'll just put that some constant out here. Anyone know what we do with e to the ix? Everybody here is past the 48C or equivalent, right? Remember de Moivre's theorem? De Moivre. I'm not good. It's probably got an accent. Or was it Euler's? Euler's. Anyone? No? Well, e to the, we usually write it this way, e to the I theta is equal to what? I sine theta plus cosine theta, or do I have the I in the wrong place? Okay. So if the discriminant here is less than 0, you have a complex solution, but that's okay. It's just a sinusoidal solution, right? If it's positive, if it's not complex, right? It's either going to be an exponentially rising function or an exponentially falling function. All right, let's do a real problem. Okay? Filling up blackboards here. Okay, let's take a look at this much simplified problem here. Second derivative of y plus 5 times the first derivative plus 4 times the function, a nice linear differential equation, is equal to 0. And my initial conditions are y0 equals 0 and y prime of 0 equals 1. Did you have a question you want to share with the class, or no? Okay. All right. So first thing is we want to look at the associated polynomial. We get the coefficients from here. I'm going to use x because I think that's a little simpler. X squared plus 5x plus 4 equals 0. We could use the quadratic formula, but it looks like this is just x minus 4 times x minus 1. So my roots are 4 and 1. And the general form of the equation is a times e to the, these are pluses, these are minuses, e to the minus 4x plus b times e to the minus x. All right, here's where my initial conditions come in. All right? If y of 0 is equal to a plus b is equal to 0, all right, I have a little information about a and b. The derivative of y is negative 4a e to the negative 4x plus negative b e to the negative x. And if the derivative at 0, well, what's that? That's minus 4a minus b, that's equal to 0. So now I have two equations and two unknowns. Just add them together. I get negative 3a equals 0, or a equals 0. That doesn't sound right. I've done something wrong here. Oh, sorry, this is equal to 1, right? Still isn't working quite right. Oh, yeah, because when I add them together, you get 1. All right, so a is equal to negative 1/3. And that means b is what? 1/3. So the solution becomes negative 1/3 e to the negative 4x plus 1/3 e to the negative x. So that's our solution to this differential equation with these initial conditions. Are there any questions about this? This is pretty straightforward. It's new, but it's just using algebra and a little calculus. Okay. We almost know everything we need to know about these equations, these linear equations. However, there's one situation we haven't looked at. What if instead my differential equation was y double prime minus 2y prime plus y equals 0? That gives me an associated polynomial of x squared minus 2x plus 1 equals 0, or x minus 1 squared equals 0. So I have two roots in a sense, but they're both 1. So I know that y equals e to the x is a solution. But I'm used to two solutions. So the question is, what's the story? Am I just stuck Or is there more? Well, it turns out that when you have a duplicate root, there is more. In this case, the general solution will be a e to the x plus b times x e to the x. And if the root was duplicated 3 times, I'd have another term, c x squared e to the x. I want to verify that, because I'm not going to prove this, but I at least want to verify this is true for this equation. So let's take a look here. Y prime is what? It's a e to the x plus, now I'm going to have to use the product rule, b x e to the x plus b e to the x. All right? And now I need the second derivative. It's going to be a e to the x. Well, I have to do that again here. B x e to the x plus b e to the x plus b e to the x. Okay? So we'll start over here. A e to the x plus b x e to the x plus 2 b e to the x. That's my y double prime. Minus 2 times the derivative, right? Minus 2 a e to the x plus b x e to the x plus b e to the x. And now just plus the original function, which is a e to the x plus b x e to the x. Okay, so I've got 1, 2a to e to the dx's, but minus 2, so they cancel. I've got 1, 2bx e to the x's, minus 2 of them. These cancel. And I have 2b e to the x's and minus 2b e to the x's. These cancel. Equals 0, just as I hoped. Okay. Let's try a few of these. On this handout, just the first page, I have 3 problems for you to try. Make believe it's the SATs and don't turn the page, right? Or if you want, you can turn the page. Oh, and one more for Kim over there. All right, everybody take a shot at these 3 problems and see what you come up with. Just double checking, Richie's did not get here, Andrew's not here, Kevin is not here, and Kenneth Wong is not here. And of course, Park is not here. I'll be back in just a minute. Okay. Number one looks fairly familiar, doesn't it? Except for the initial conditions. Does anyone have a solution to number one? Are you willing to share? Go ahead, Sam.
I was actually going to say, I don't think I got this right because I kept getting a 0 for B, but I had y equals negative e to the negative x.
Okay, well, let's check it out. Let's do an initial condition on it first. So y of 0 equals -1. Y prime equals e to the minus x. So y prime at 0 equals 1. Oh, so that's good. Okay. Y double prime equals negative e to the minus x. So we want negative e to the minus x plus 5 times e to the minus x plus 4 times minus e to the minus x. Well, that's really obviously 0. So that has to be the solution. Very nice. You notice I didn't solve it, I just showed that it was correct. Are there any questions on that one? Okay. How about number 2? Does anyone have a proposed answer, number 2? Is this harder than I think it is, or, I mean, I realize it's new. I saw someone shaking their head up and down. Yes, it is harder. Okay. Let's take a look. Y double prime plus 2y prime plus y equals 0. So, the associated polynomial is x squared plus 2x plus 1 equals 0. This is clearly x plus 1 squared. Oh, one of those duplicate roots. So that would make the solution y equals a e to the minus x plus b x e to the minus x. now we have to check these initial conditions. So if y0 equals a plus, goes away, is minus 1. So we have a already. And then y prime equals negative a e to the minus x plus b, negative e x e to the minus x plus, wait a minute, I'm gonna do this wrong. E, so it's x times the derivative of e to the minus x, which is negative x minus x, plus e to the minus x times the derivative of x, which is e to the minus x. And that's supposed to equal, at 0, well, we know a is minus 1, so we can plug that in. And at 0, this becomes 1. Plus b, okay, this goes away at 0. So this is just 1. And that's supposed to equal minus 1, which says to me that b equals 0. So that suggests the solution is just y equals minus e minus x. Should we check that? Let's see. At 0, it's minus 1. Derivative is e to the minus x. So at 0, at 0, that's 1. Okay. Wait a minute. Wait. Hold on. Wait, I did this second step wrong. Y prime at 0 is 0. So b is equal to 1, right? Yeah.
Why is a equal to negative 1?
Okay, so this is the general form, right? So if I plug in 0, this becomes 1. That's a. And this becomes 0. And I know at 0, the function is minus 1. So that's all that's left is a equals minus 1.
Is this 1? It says 1.
Oh, I can't read and talk at the same time. Yeah, thank you. I'm looking at all these problems look the same, and I keep pulling off the wrong numbers. All right, hold on. Maybe I should have just written it up here. Y sub 0 equals 1. Y prime of 0 equals 0. Okay. So a is equal to 1. So let me start over here. So y prime at 0 is negative a, which is negative 1, plus b. This goes away. And at 0, this is 1. So that implies b equals 1. So a equals 1 and b equals 1. All right, I messed up so much. Why don't I go through this? So this should be e to the minus x plus x to the minus x. So let's see. At 0, this is 1. The derivative is minus e to the minus x plus x times the derivative of that, which is negative x minus x plus e to the minus x. So at 0, this becomes -1, this becomes 0, this becomes +1. So this becomes 0. So the initial conditions are right. Now all we have to do is see if it actually fits the equation. So the second derivative becomes e to the minus x plus, well, this is going to be minus e to the minus x, so those are going to cancel, plus minus, oh, that can't cancel. Hold on. Oh, no, I don't know what I'm doing. I have to plug this in over here, which I'm not even ready to do. E to the minus x, this is minus e to the minus x. Okay, that's fine if that's going to cancel. So this is x times the derivative of that. So that's x e to the minus x plus minus e to the minus x. I think that's right. Take that away, x, that makes that negative, and that's positive. Okay, so now let's just add it all up. So, these are going to cancel. And these are going to cancel. So x e to the minus x minus e to the minus x, that's this, plus 2 times this, minus x e to the minus x, plus y e to the minus x plus x e to the minus x. Okay, so 1, 2, minus 2, those go away, and these are opposites, so they go away, so it's equal to 0. So that's absolutely correct. Okay, why doesn't everybody take a break, and we'll come back and we'll look at an application. If there's a difference, well then you would get R2 equals R3, and you just get 1x for that R1. Correct. Okay. Okay. We didn't go over number 3, and if you go through it the exact same. If you go through it the exact same way you went through 1 and 2, you run into this problem that your solution is a complex number. There's an alternative route, which is a little more direct, which is, I mean, first of all, this a here, it's just a constant, right? So you can get rid of that, right? So you really only have to look at a bi x, times some constant plus b e to the negative bi x, right? But a quicker solution is to look at the discriminant, which in this case is 16 minus 4ac 20. So that's just 2i. Right? Now, if the discriminant is less than 0, you get an imaginary number. And then instead of writing this as e to to the b here, right? Instead, you would write it as y equals a times sine, and then 2x plus b cosine 2x. I think that's right. So let's just try that here. If y sub 0, well, the sign goes to 0, so we just have b. That's equal to 1/2. And then we need the derivative of this, which is 2a cosine 2x minus 2b sine 2x. Right, that's y prime. So y prime at 0 is just 2a, which is equal to 1. So a is equal to 1. So that should be the solution here, except I don't think I did it right. All right. We're going to stop now with this. You can play around with number 3. I'll post a solution probably tonight or tomorrow. I would like you to make the rest of this worksheet that you haven't completed, make it part of the homework due next Thursday, right? And you can come in on Thursday with questions if you have. But I would like to work on a new topic right now, which I think is really, it's a good application of differential equations, but we're only going to use things that you should know. So let me get started on that. The topic is called orthogonal trajectories. Orthogonal trajectories. Now, this is already a little confusing, so let's simplify it a little. Can someone tell me what orthogonal usually means? Orthogonal. Uh-oh. Well, this is an important mathematical vocabulary word. Orthogonal, when you're talking geometrically, means perpendicular. I say that because there's circumstances where there is no geometry, but we still have orthogonality. Okay, so we're looking for something which is orthogonal to something else. So the first trivial example is going to be x squared plus, we're not even going to do this with math. We're just going to say x squared plus y squared equals a squared, where a is some constant that varies. Right, so, or you can think of it as a family of curves. In this case, these are circles. They're concentric circles. So the question is, geometrically, what is the family of curves that is always perpendicular to these circles? Now, this might not be obvious, but you have a line that goes through the center. Well, the line segment to the circle is always a radius. And you may recall from your high school geometry that a radius is always perpendicular. to the circle. So all of these lines that go through 0 are orthogonal trajectories. Now, this is such a simple example, you don't really need to calculate it. The question is, let's say we have a family of curves, and we want to find an orthogonal trajectory. How would we go about doing that? So we're gonna do an example here. We're going to take a fairly simple family of curves. We're going to take the curves described by this equation. X equals k, some constant, times y squared. So let's think about what that would look like. Assume for a second that k is positive, right? This is a parabola on this side of the y-axis. It's a family of parabolas whose curve depends on k. But if k is negative, then these are just reflected over here. You might say to yourself, well, that looks like a daunting task. I want to find some kind of curve which, for every one of these parabolas, is perpendicular, right? And I want to find out what that is. Okay. Well, when we say perpendicular, of course, none of these are straight lines, right? So it's just, we want the tangent at this point to be perpendicular to the tangent at this point. So how do we find the slope? We find the slope of a curve at a certain point. Well, we find the derivative, right? So here we don't have a function, but we can still find the derivative at a point by using what? What kind of differentiation? So here I heard implicit differentiation. I simply find the derivative of both sides with respect to x, right? So the derivative with respect to x of x is just 1. The derivative with respect to x of y, well, there's a constant that just stays there, times 2y times dy dx. So now I can solve for dy dx. Dy dx is just equal to 1 over 2k y. That tells me the slope of every point, right, given the y coordinate, tells me the slope. Now, given a slope, how do I find a perpendicular slope?
The line times is equal to -1. The two lines times together is those of two lines.
Negative reciprocal. I'll write that down. negative not a good speller, that's why I went to math. I think it's an A. You know that if I have a line and say the slope is 2, right, m equals 2, that a perpendicular will have a slope of negative 1/2, negative reciprocal. Okay, so the m I'm looking for here is negative 2k y over 1, or negative 2k. So what I want is a function, or a family of functions, where this is the slope. What's the slope of a function? Its derivative. So dy dx equals negative 2ky. Now that looks like what?
Use it both sides, like remove the y to the left and the dx to the right, and integrate both sides.
Yeah, we're getting there. Yes, thank you. This is a differential equation, right?
Yeah.
That's what we've been studying, right? Let's do as described. I want to leave a little room here to keep this nice picture up. Okay, so we're going to separate the variables, right? So we get y. Oh, no, we're not ready to do that yet. Because it would be nice to get rid of this k. And the way we're going to get rid of the k is we're going to solve for k over here. K is just equal to x over y squared. So this is negative 2x over y squared times y, or negative 2x over y. Okay, now I want to separate variables. So I'm going to get y dy equals negative 2x dx. Let's integrate. Here I'm going to get y squared over 2. Here I'm going to get negative x squared plus some constant. And finally, I'm going to add x squared to both sides, and I'm going to divide by c. So I'm going to get y squared over 2c plus x squared over c equals 1. What is that the graph of? Y squared over 2c plus x squared over c. Anyone? You have to remember all that math you learned in high school, right? This is an ellipse, right? If these two were the same, it would be a circle, but it's an ellipse. It looks like the major axis is on the y, and the minor axis is on the x. So if I may put my artistic talents, my notorious artistic talents to work. Sure enough, I'm not just drawing ellipses here. I'm drawing a curve which is perpendicular to every one of these. given some imagination. What might this be useful for? Well, some of you are going to be physicists or engineers, and if you know a little bit about electricity and magnetism, electric fields and magnetic fields are often perpendicular. Right? So if you know the equation of the electrical field lines, then you could find here an equation for the magnetic fields. There's another application from mathematics. Okay. Let's try another example. No, I have no more examples. I only have a worksheet. So why don't you take a stab at number 6, and if you get through that, number 7. And while you're doing that, I'm going to see if I can't draw a picture of what you're solving here. How's that? Okay. Okay, so it's similar, but these are not parabolas. This is the square root of x cubed. I guess to find the orthogonal trajectory looks like I'm going to have to do the problem. Okay. quite sure what I got here. Oh, I see. Yeah, I did the wrong thing, okay. Actually have this. It's more like anyone gotten an ellipse again? Anyone have a solution they want to share? It's such a timid class here. So I haven't like taken anything away from anybody who's gotten something wrong yet in class. They have to go out there and take chances when it's free. All right, let's try this. Let's try the math here. So the equation is y squared equals x equals kx cubed. So if I implicitly differentiate, I get 2y dy dx equals 3kx squared. If I solve for dy dx, I get 3/2 k x squared. And if I find the negative reciprocal, m for my orthogonal trajectory is going to be negative 2/3 k over x squared. But I'm going to solve here for k. K is y squared over x cubed, and I'm going to plug that in. 2/3, well, I get y squared on the bottom and x cubed on the top times x squared. So that's going to be negative 2/3 x over y squared. And so my differential equation is dy dx equals negative 2/3 xy squared. And so I get y squared dy equals negative 2/3 x dx for y cubed over 3 negative, oh, the 2 is going to go away. We get x squared over 2. And so y equals, let's see, 3. Wait a minute, this was 3. 3's go away, yeah. That's nice. Equals the cubed root of negative x squared. And cube roots don't have that problem. We can just bring the minus out. Yes?
I think the original sentence is over 2y, like on the left there.
Tell me where my mistake is.
On the third line,
Here?
should be 3 over 2y. Right.
Oh, thank you. Okay, so we have another y here. We have y cubed here. Cubed here. Y cubed here. Am I doing okay? Y to the 4th here. 3 doesn't go away. So y equals, uh-oh. That looks really bad. If that's correct, that's really bad, because I can't find the 4th root of a, that would be imaginary. Let me check again, this thing. 2y squared 2/3 y over x squared, that's right. Oh, wait a minute, okay. Thank you. So negative 2/3 y over k x squared, negative 2/3 y over this, which is y squared on the top, x cubed on the bottom, is x squared, minus 2/3 k, oh, just x and y. Ah, that looks much better. Okay, so dy dx equals negative 2/3 x over y. So integral y dy equals integral negative 2/3 x dx, or y squared over 2 equals negative x squared over 3 plus a constant, or y squared over 2c plus squared over 3c equals 1. So it's another ellipse with a little different shape. Thank you. Okay. So, again, I'd like you, for the homework, to add, you can do that last problem. And when you hand in your homework, even though it doesn't say name on here, put your name on it. It's not due till next Thursday. Okay? Don't put your books away. All right, whatever. I do have a topic that I want to discuss in just the last few minutes. You need not take notes, because this will not be on the final. And if you want to keep yourself as far away as possible from mathematics in the future, then you would be best to smile and ignore everything I'm saying. But I just want to see if I can give you people in the remaining 10 minutes just some idea of why once you get to the next level of mathematics, it gets kind of exciting. At least I think it gets exciting. Mathematicians are interested in differential equations and integration and all this other stuff, but really what we're interested in is patterns. Things that have patterns. And so I want to show you a pattern which you've already seen and you're already familiar with, but you don't realize how important this pattern is. So I want to talk to you a little bit about the topic that may seem kind of crazy for this course. It's kind of a 48C course. Although if you go on to Calculus 1C, you'll have to come back to vectors. But I just want to mention a few things we know about vectors. We often write a vector like with a little arrow on top. And if I have two vectors, I can always add them, right? And I want to be explicit here. I mean three-dimensional vectors, the ones we learned about previously. I say that because I'm going to change the meaning of the word vector about halfway through. So we also know that if we have a constant, which is a real number, and we have a vector, that constant times the vector is also a vector. We have a special vector which we call the zero vector, which has a special property that if you add it to a vector, you just get that vector. And we have some other properties, less important maybe, not really. We have a distributive property that says you multiply a constant times a sum of vectors, that's the same as the sum of the constant times each of the vectors. And in mathematics, we have a very general name for objects like these 3D, they're kind of pointy arrow things, right? We're calling vectors. We have a name for this, which shouldn't surprise you. It's called a vector space. But when mathematicians study a vector space, they're not really that interested in whether or not these are, these kind of pointy vectors that you add this way. What they're interested in is objects which have these properties. Now, let me just say one more thing about vectors, which you may remember. We have something called a unit vector, actually. And in fact, we sometimes talk about the unit vectors I, j, and k, which are just vectors of length 1 in the x, y, and z direction. That's my I, j, and k. And the nice thing about dealing with these unit vectors, these perpendicular unit vectors is, you know, any vector can be described as a linear combination, there's that word again, of I, j, and k. And we have a special name when we're talking about vector spaces for vectors where this is the case. We call this, and this is a new vocabulary word, we call the vectors I, j, and k a basis. Now, in fact, a basis has to have this property that you can make any vector from it, but it needs another property, which is it's as small as possible. In other words, if I invent some other vector here, we'll call it jkl, right? And I plug it in here, L is not part of the basis, right? Because it's redundant. You don't need it to make every vector. Now, it turns out that the number of vectors in a basis for a particular vector space is always the same. In this particular one we're used to, we have 3 vectors, right? And we give that number, 3 in this case, a name. We call it the dimension. It's the dimension of the vector space. That kind of fits. You think of 3 dimensions, right? We only have I and j, we have 2 dimensions. Right? But mathematicians define the dimension as the number of vectors you need in the basis. Okay. I hope I'm just reminding you of stuff, right? There's nothing new here. But now I want to point out something to you. We were talking about linear differential equations. And you'll recall that I said, well, if you have a, you know, I'll just use 2 dimensions here. A second order equation, the solutions of this, you have 2 solutions, right? You have y equals e to the r1x, y equals e to the r2x, unless r1 is the same as r2, and then you get this y equals xr e to the x, or x, sorry. Well, you probably haven't thought of this before, but you could think of these solutions themselves, a solution as a vector. Now forget what your idea of what a vector is. It's this pointy thing. Just think of a vector as the name of some kind of object. So here I have an equation, and I have 2 solutions, but actually my general solution, of course, is just a linear combination of the solutions. Any solution is a linear combination of these. All right? And in fact, these 2 solutions make up a basis for this vector space. This is a very unusual vector space for you. It has nothing to do with pointy arrows. It doesn't have anything to do with geometry necessarily. It's just, we're calling these objects vectors, and we say, do they fulfill these requirements? Well, we know we can add any 2. We know we can multiply them by a constant. That's that linear combination thing. What about the 0 vector? We need a 0 vector. What would be the 0 vector? Well, y equals 0. Right? Doesn't that fulfill this. All its derivatives are 0, right? If we add this to another solution, we get that solution back. Okay. So in this case, you can see right away that this follows the same rules, and in fact, thankfully, even when the roots of this equation are duplicate, we still get another linearly independent solution. And we can assign to this a dimension. A second order linear differential equation has dimension 2. Right? So, I don't want you to think that there are like two kinds of vectors in the world. There's the solutions to differential equations, and then there's the pointing ones. There are lots of different vector spaces with all kinds of mathematical objects in them. All they have to do is follow these rules, and then we can call it a vector space. And one of the really cool things about mathematics is if we study this abstract idea of a vector space, everything we learn applies to all the vector spaces that we might know about. So that's not all that mathematics is about. It's not just about vector spaces. But this is what mathematicians do. Right? They take things that we've discovered, and they extract what is similar about them, and then they study that abstract idea. So, all right, well, that's what I wanted to waste your time with the last 10 minutes. Thank you for listening, and I'll be here if you have questions.